Lab 5, Faraday's Law. The lab. We are exploring Faraday's Law by measuring the time it takes a magnet to fall through a conducting non-ferromagnetic tube, in this case a tube of aluminum foil. We then model this interaction in software. The measured time to fall was 1.1 seconds, and the model time to fall was 0.23 seconds. The method. We drop a magnet through a tube of aluminum foil, the same magnet as used for Lab 3. We then model this interaction in a color by numbers glow script template. Specific physics principles and how they apply to our experiment. Note that I will be referring to coils of wire as opposed to whole tubes. This is because we actually model our tube as a bunch of stacked coils. So, firstly, Faraday's Law. Changes in magnetic flux in a coil create an induced EMF in said coil. Here, as you see in picture 1, the falling magnet with the velocity v gets closer and closer to the coil, thereby changing the magnetic flux through it. This magnetic flux and the EMF can be modeled using the equation shown on the screen. Using this EMF and Ohm's law, we can now calculate the current inside of the coil using V equals IR. Next, we can use the Biot-Savart law to calculate the magnetic force that the magnet applies to the coil. As you can see on the screen, the magnetic field, B, produces force F at a slight angle. All of these forces together create resultant force R on the entire coil. The force is modeled using the first equation under Biot-Savart law, F equals I delta L cross B, and the B field is modeled using the equation we previously used in Lab 3, the derivation of which I once again leave as an exercise to the viewer. Finally, using Newton's second law, we know that any force that the magnet applies to the coil will be applied by the coil to the magnet. Therefore, this resultant force R, here represented once again as the letter F, is applied equally but in the opposite direction to the magnet, thereby pushing the magnet upwards. We can now just stack these coils one on top of the other to create the same effect, but with a much greater magnitude and over a much greater distance, as there are tons and tons of coils. Here is the model in slow motion glory, using the equations on the left. The first question. The intensity of the coloring on the tube represents the magnitude of the current, and its color represents direction. We know that the current must be flowing counterclockwise when viewed from the top, as this counterclockwise current would create an upwards magnetic field, resisting the magnetic field of the falling magnet, or rather the change in magnetic field, as by creating this magnetic field, it is lowering the change in magnetic field. As we know that a counterclockwise current would be required for this behavior, and this is the behavior we observe, we can conclude that this red light is indicative of a counterclockwise current. If we flip the magnet around, the current would now be clockwise and blue in color. However, everything would be otherwise the same, as though the falling magnet would have a reversed magnetic field, so would the magnetic field generated by the coils. This is because, by Faraday's law, the generated EMF, and therefore the generated magnetic field of a coil of wire, will resist the change in magnetic flux. As here, the change in magnetic flux is just an increase in the magnet because the magnet is moving closer and farther away. The magnetic field will directly resist and be opposite to the magnetic field created by the falling magnet. The total time in the tube between the model and the actual experiment are incredibly different. This appears to be a problem in the calculation of magnetic flux and magnetic force in the computer model. It is unclear what exactly is the cause of this. The computational system could be more accurate by rectifying this issue, as right now the computational system tells us very little about the actual real-world behavior. Here is the velocity time plot for the computational model. As our computational model had the issue we just discussed, it is not a very useful plot. However, we can imagine what a plot would look like with a functional model. It would look something more like this, the red line, with the magnetic force increasing and continually resisting more and more of gravity as velocity increases, as velocity is a component of the EMF, therefore the current, and therefore the force on the coil, and therefore the force of the coil on the magnet. In effect, this force is a braking force, acting a lot like air resistance, increasing with velocity. If the resistivity of the conductor were reduced as close to possible as zero, the current induced into the coils, and therefore into the entire tube, would be effectively infinite, slowing the magnet much, much more, and, indeed, with a close enough resistance to zero, it would even throw the magnet far, far away from it, as the magnet moving even slightly towards it would induce a massive current, thereby creating a massive resistive force, throwing the magnet incredibly quickly upwards. If holes or slots were cut into the tube, this would affect the model in different ways. If these were horizontal slits in the tube, then it would be effectively like removing coils, therefore the magnet would move faster in some parts of the tube than others. Vertical slits, on the other hand, would not have terribly much of an impact, as current could merely flow around them. I don't even know what I'm doing. I'm just gonna leave this in. Honestly, whatever. What do you call it? The code's in the video description. Yeah. Thanks for watching this train wreck.